So next up, Bogdan Doroslovac will take us dancing in the dark.
Okay, so first of all, before you start throwing any tomatoes, this is a Windows machine, and thanks for making it work once again. Few questions. Anybody here familiar with inertial navigation? Okay, with general concepts like transformation matrices, quaternions? Okay, super awesome. Anybody flat Earth believer maybe? Okay, depending on the model. Well, basically, first, before I start, I would like to thank my colleague once again for trying to make badges, like sort of a takeaway for this workshop that we in the end didn't manage to push through because of some technical reasons. They should have supposed to have an ESP12 with MPU 9260, so quite a precise accelerometer, gyroscope, magnetometer, 9 EMU. Well, you can help still the PCB and try to make it work on your own, but it was quite a challenging thing, and we almost made it. Now, so something about myself. My name is Bogdan Doroslovac. I currently work in Zuka Engineering here in Serbia. I'm an advanced embedded engineer. And before that, I was doing some maintenance in the aircraft industry, mainly in the ATA chapters 22-34, which are autopilot's navigation systems. And before that, even, I did some R&D in military company here in Serbia, working on an advanced light attack system with the autopilot and stuff there. That was my first ever job, super awesome, and there I fell in love with inertial navigation. Now, so I'm not a big Bruce Springsteen fan actually, but somehow the name of the topic came by itself, because how the dancing in the dark, basically that's sort of a romanticized version of what I see as inertial navigation. We don't have any external references. We are only reliant on our look and feel, and we are trying to navigate our best way there. And since this year's Balsicon was all about finding yourself, I think I took it the most literally here out of the whole bunch, and you will see how to find yourself and how to know where you're heading without any additional external references. Well, at least for some while. So, first of all, what is generally navigation about? Navigation is the concept of knowing where you're going. Well, duh. But more than it has quite some interesting properties. Basically, most of our navigation can be done in two fashions. One being other, or any sort of, let's call it referent navigation. Navigation where you have references like stars, like maybe beacons. Radio beacons were used for ships, or GPS, or GLONASS, or any sort of those Baidu, Galileo, GNSS systems. Anybody familiar with the concepts of GPS systems? Okay, so you know that there are two limitations that are mostly dominant for the GPS system. One is, well, it's a thing owned by the American government. Like GLONASS is basically owned by Russian government, so there is no guarantee of data precision at any moment, or the availability. There is some push these days to get at least the civilian GPS to be fully available, so L1, L3 satellites. Second of all, any GPS that's more precise than some range that I forgot, that can measure at more than 10 Hertz, that can travel at more than some 500 meters per second or above 10 kilometers, is considered ammunition. And therefore you cannot easily trade it, you cannot operate with it, and you cannot resell such equipment. There are FPGA implementations which are quite interesting, but they also have limitation by the sheer design of the signals and GPS. Other types of navigation are out of dated, so maybe somebody will, out of sheer change of heart, pull his sextant out in the middle of the sea, but you typically don't expect to see that these days. On the other hand, like we also heard in Zoz's talk yesterday, inertial navigation is pretty damn precise when done correctly. You cannot interfere with it. It's based on intrinsic properties of our universe and how we work and physics. And it's passive completely. You cannot interfere with it in any reasonable way. You would have to have hardware access to it. And if we're talking about fast-moving vehicles like, let's say, rockets, you have pretty slim of a chance of getting it just to interfere with its GPS. If you're getting it, you have other means of getting it in the first place. So, reliability is the key aspect. Also mentioned in the ZOS lecture yesterday, it was the aircraft GPS. Typically, let's say Airbus will have what's called an ADIRO unit, so Air Data Inertial Reference Unit, or actually 3 of them, which will correlate and try to find where you are going, where you are heading, and error should be slim, up to 0.1%. And it's considered, again, ammunition, tactical resource. You cannot get those components off the shelf. And one more thing that's good about inertial navigation, you can go at extremely high rates. For analogous systems, you basically have no speed limitation. You can measure at the rates which coincide with your sampling rates, or even better, if you are competent enough, you can make a fully analogous system using those properties. Well, negative effects are that it's quite hefty in the price tag, especially for the more advanced version, which we'll cover later. And once you're lost, you're lost. You have no way of recording your course. You have no way of actually knowing how it correlates with the real world. And typically it will be a scenario of analysis in a post-mortem analysis. So once everything failed, you'll see how and why it failed. Typically it will be self-evident, simple and stupid, but at the point in time when you are doing that, that's quite hard to expect. And one of the key issues in any such system is calibration. Typically it has to be done per unit, per piece, and there is no easy way around it and no easy way just doing it right. It's a lot of crazy math. Now, how the navigation actually works, let's take a step back to look at some classics of physics. Anybody here familiar with the second Newton's law? Okay. Anybody here knows this formula? Well, anybody here knows that it's actually wrong form of it. We are taught this in school as a second Newton's law. It actually sounds a bit different. And this is with some assumptions. And please be careful about those, because precisely those assumptions make rockets fly. And if you look at it, we define force as thing giving an acceleration to the mass. In turn, acceleration is nothing but change of the velocity, which in turn is change of the position. And we have a way of getting the acceleration. And just by simple integration, turns out not to be so simple, but by simple means of integration, we can get back to where are we going. Now, how much of you forget the constant while integrating? While preparing this talk, an interesting thing, I made a small Octave demo for you, shifted from MATLAB to Octave and some sort of rotation and so on. And I spent 2 hours troubleshooting the thing that I missed. Initial conditions, therefore I missed constant, and it took more than expected. So high school physics getting a revenge on me. Now, the accelerometer is a device that can measure specific force. Why this is important? It can measure something that we think it's basically force causing the movement of the object. Why specific? Because somehow gravity is also there. And funny thing, I don't know if you know it, but accelerometer standing still will actually measure the G, all through not moving. And if you throw it in the air, it will happily measure the zero acceleration. while it's in the free fall, so in sort of the apogee. Why it's that? It's because accelerometers are actually measuring the total force applied on the object. Now, what you know of the gravity is also a bit wrong, because turns out it's not as simple as one might think. Well, gravity should point straight down, and it's not. It's pointing a bit slanted, because there's a thing called centrifugal, centripetal, I won't get into it, force, because if I say either of the two, I think somebody will burn me. Anybody in the camp for the centrifugal force here? Centripetal? Okay, glad. Now, I'm glad it's so. Regarding the flat earthers, based on the distance you want to cover, a gravity model might change a bit. So if you're talking some, let's say, navigation a few kilometers away, we can happily agree all that the Earth is flat surface, completely flat. You may feel free to throw any tomatoes at me now. Please don't. And that gravity is a homogeneous field pointed down, whatever down may be. And the Earth is also like suspended on 3 elephant trunks and so on. If you want to go a bit further away, you need to use what's called spherical models. So something that we learned in school, just a big blob, pretty round, pointing towards the center, but it turns out the Earth is not completely round. It is actually more of the elliptical shape, rotational ellipsoid. Even funnier, that is also not the case. And if you want to go really, really long range, or really, really precise, like intercontinental ballistic missile precise, you have to factor in everything. And mathematicians have a way around it. They first went about, well, okay, there is something that is more closely related to an Earth, and that's an Alpeoid model, which turns out just also not to be correct. And there was like a super auto-referent definition that there is a geoid, whatever you want to call it, that is basically the mathematical shape of the Earth. So Earth is a shape of the geoid, and geoid is precisely the shape of the Earth. If the Earth changes by any means, the geoid also changes to follow the Earth. And I think that's one of the best recursive definitions that I've heard. And because of all that, finally in the year 84, so 3 years before my time, there was this bunch of smart people decided to make a standard out of it. And basically what it is, it's a referential ellipsoid with the gravity in all the possible places. So, like doing anything with the constants, don't be too smart about it. Go for this one. It's simple. You just punch in the latitude, longitude, altitude, and you basically get your effective gravity back. If you try to calculate, to compensate, to do anything, you will surely fail. You will be closely failing, but failing nonetheless. Now, there are various types of accelerometers around, and I listed some of the devices that I am not even sure how they work. Like just yesterday I found out about heated gas accelerometer, which is quite an exotic technology. Basically bubble of gas that is heated in the center, and then based on the acceleration the temperature flux will change, and that can be detected. One of the prime versions of the accelerometers widely used today is MEMS. MEMS is basically so it's micro-electrical mechanical system. A tiny little thing, basically a quartz crystal on the substrate, that based on the acceleration will give out some voltage. And widely used are the one in phones, with dimensions ranging in millimeter ranges. Big accelerometers tend to be like this big. And why do we need them? and where do we need them? That's the top priority question. We can only use accelerometers in referential planes or in the inertial planes, which are completely static to the universe. There is one such plane, and I will throw a lot of slides. I won't read them through. I don't think that's necessarily, but eventually if you want to follow it and do something based on this, maybe it will serve a purpose. Now, there's an inertial system. This is ideal construct of an Earth static within the universe, everything else rotating around it. And basically what it does, it's there so we can do all the math nicely. In this system, second Newton law actually applies. In system where we are standing, it does not, because it's not inertial. It does not in the form that we know it. It applies with applying additional elements like the Coriolis force. Now, you'll notice here one interesting aspect again. North. There's a concept of true north. Why true north? There are actually many norths to begin with. What you see when you get your compass out, it's a magnetic north, which is highly imprecise if you're getting close to the pole, which, by the way, also not only is imprecise, is shifting over time. So a lot of things like Adirus have to compensate with magnetic variation or Magvar tables, and so on. And finally, it's not easily doable to have a precise magnetic navigation device because a lot of soft iron and hard iron problems with it. If anybody has tried doing magnetic navigation, you will know that just having a screwdriver nearby will mess your readings tremendously, because planet is in some millimicrotesla ranges, and it's so damn weak that basically just any sort of magnets, which we now have in abundance, especially the strong neodymium few Tesla types, will easily mess with. Second type of north is geomagnetic north, which is the approximation of what we think magnetic north should be and where it should be most oftenly. It's again just nice concept for the astrophysics, but for navigation does no purpose, and there is only one true rotational north, which is the axis among which planet spins. You cannot determine that by magnets. That's completely impossible. You either have to know it, or you can use some smart methods. So, another reference system that we use is basically the Earth center Earth fixed system. It is the same as inertial system, but with a tiny quirk of rotating with the Earth. So the only difference between inertial and ETSF system is that you just have to apply angular rotation to it among concretely in this case, the true north axis or the Z axis. Now, those were all global systems and did not help to determine where we actually are. So we need additional thing. We need something which is local. And based on the literature that you're using, you will find that typically in the West, you will use the northeast down referent plane, or in the East, especially with the Russian authors, you will use the east-north up coordinate system. Reasons vary. One of the prime definition is basically that depends which army type used it the first. So if you're looking at artillery, they will typically use the ENU. If you're looking at aircraft modeling and so on, they will use the northeast down. They are completely analogous and easily to go between. And finally, we have we need somewhere to position our accelerometers and to start integrating. We have our body coordinate system. Here there's quite a nice rockety thingy. And the idea is that basically we are always in the Cartesian referent plane. So we have 3 axes of freedom. To cover that, we need 3 accelerometers. And now we have a problem. It turns out that we only know how our our center of mass is moving. we don't know anything about the whole body structure. And that is precisely the 3 degrees of freedom navigation versus the 6 degrees of freedom. Historically, first ever guided rocket, FAU-2, to use accelerometers and to use guidance, actually used the suspended gimbal gyroscope platform for that. So what it did, it had a hollow area inside it and suspended accelerometers so that they are free and that you can all the time have the platform static relatively to the outer shell of the rocket and basically integrate your merry way through it, through the flight, and hopefully hit the London at that time. But now, in modern systems, we don't use such gimbaled contraptions because it's highly complex and highly expensive. The typical approach is to use the strap-down navigation system, which what it does, it does all the calculations and basically forms a virtual platform which is analogous to one being in the middle. And it does it so by constantly rotating the thing. These are some referent matrices, basically in order to be able to rotate about axis you need to use this. Anybody familiar with the 3D graphics will notice that it is pretty much the same as you use to rotate images. And even navigation is actually simpler because skewing is not possible for rotation matrices. There is no scaling, there is a lot of these eigenvectors, cool features. You can forget all that and just use simple rotation and translation. And typically Euler angles, how they are called, are named alpha, beta, and gamma. But much more widely used, and the thing that I'm citing here, are roll, pitch, and yaw, which are basically the 3 properties of the body navigating. So the roll is being the rotation among its dominant axis, so typically about axis of a symmetry, let's say, of a missile. The pitch will be its tendency to go up and down, and the yaw will be its tendency to go left and right. And you'll notice that in missiles it is decoupled, while in aircraft it's highly coupled. It's typically roll and yaw. You cannot that easily shift that system. Now, okay, so how do we get our strap-down navigation working at all? Well, there is this Euler angular formula, which is quite analogous to Newton's second law. Basically what it does, it dictates just how you can find out what is your current angular acceleration by the means of knowing the inertial moment, which is the fundamental inertial criteria for the body, or fundamental property, like mass is for the point. And basically you just calculate all the outer forces that are affecting you. You will notice that here we just can stop on the first integration, but we can discuss it. And now we've got all 6 equations, everything there that we need. And how do we proceed about it? Well, we just integrate our merry way along. One interesting property here. How many mechanical engineers are here? Super awesome. So what's interesting here? Symmetrical systems, or highly symmetrical systems, are much more easier to compute than non-symmetrical ones. So inertial tensor, the matrix, big blasted thing there, tends to degrade to a smaller vector if you are using missiles. So there's a lot of good things going simple. So aircraft would not be as simple as a missile. Now, for the programmers out, it's not all hardcore math. It turns out that we can just discretize. What does it mean? Basically, what's an integral? Integral is nothing but the cumulative sum, and that's it. If you're fast enough, if you're precise enough. You don't have to be super smart about it, you don't have to estimate it, you just have to be at least 10 times faster than the response of your system. If you are good there, and if you can provide that speed, you're safe to integrate, and that's it. Also with the derivatives are nothing but the sample over sample changes. The discrete derivative is just that. You just take the two values and look at them, how they are. Now, for the angles, we use gyros. And gyros are extremely interesting piece of technology. They basically fall into two types. One being the absolute gyro, or the position gyro, which is what you know as a spinning top, a thing trying to stay in the place as it was. And the other one being the rate gyros, which are actually telling you what the rate of the movement is. I didn't want to go fully exotic for these gyros, so I just chose some types. Here there is again MEMS, so electromechanical systems. I got it right this time. There's a dynamically tuned gyro, which is super cool contraption, a mechanically balanced wheel, which has a precise precisely turned turning frequency, so it nulls all its mechanical failures. It's again expensive to produce, and it has a limited life cycle. And there are more exotic technologies like ring laser gyro and the fiber optic gyro. They are about the thing called Sagnac effect, or I hope at least the guy's name is pronounced like that. Sagnac effect is basically bouncing light beams over through the mirrors and measuring the phase shift. And basically by difference in the phase shift, you can see how you are moving. With the ring laser gyro, and it's a hefty contraption, it's basically having prisms precisely positioned and lasers. With fog or fiber optic gyros, it's a big continuous strand of fiber, optic fiber, wound in tightest possible fashion, and it tends to use up space pretty quickly. So there is less problem in manufacture than in ring laser gyro, but there is a lot more problems calibrating and adjusting for it. Now, with those gyros comes a great responsibility, and now it is quite hard to get them. You will typically be bound by laws, by the ITER law, or International Trafficking Arms Regulation, and by the Missile Technology Control Regime. There was quite an interesting debate yesterday over the civil licenses. Currently in action, there are already licenses prohibiting use of specific military use of technologies. Going for a precise gyroscope will require you to sign an EULA, which is really serious. It's not like just click next to continue. You could be really, really legally liable for what you sign there, and you will typically have to provide proof of usage per piece, for example, in the maintenance industries. And now, final thing which we hate the most: errors. They're everywhere. Everything we did now was super cool, nice, polite, spherical, frictionless, in vacuum. In reality, things degrade much quicker, so there is a lot of noise. So accelerometers tend to be noisy, even more so than gyros. There is drifting. Actually, physical drifting was firstly described precisely in the self-sustained, self-balancing platforms. People would notice that over time, gyro-gimbaled platforms tended to drift physically, or to change their position because of some small imperfections, like, for example, friction, which is actual thing in the world around us, maybe not in physics, but in mechanics tends to have quite an impact. Everything is biased, not just people, gyros as well. And there are a lot of non-linearities. You never know how the device will behave. It can even behave differently on how you are going through it, based on its bandwidth, based on things like hysteresis, so you can go one way around it, the second way when you're returning, and most of all the error accumulates extremely quickly. So let me formulate it this way. Imagine there is some small angular deviation in your virtual platform, and let's say that that's a function of time. You integrate it. So, okay, you have some f of time error. Now, imagine that there's even worse, an accelerometer, 1D. So that's t squared. If you've got 3 accelerometers, that's 3t on the third, on the power of 3, times the t. So you're somewhere in the range to t on the power of 4. So if you have any variance in your system, you are pretty much slowly drifting away and further away that you can know of. Typical mechanism of compensating this is through some filtering. Notable examples of filtering are, for example, the multi-platform approach, where basically we know that any movement is expected to be nice. So, in physics, things cannot just shift radically. And you are searching for the pattern in the noise which best fits your movement. Other than that, there is also like Kalman filtering based on external sensors, but you have to have external sensors which you can really trust, which is a problem. And I would like to show you some small thing, if it works. First of all, please do work. Okay. So this, come on. This is an actual data of 3 accelerometers. Okay. Sorry, my octave is a bit laggy today. And it will full screen eventually. Okay. Yes. This is the data that was taken from the real world gyros, rate gyros to be precise. And based of those, I won't bother you because it's really slow now. I wanted to actually do this real time, but there was so much data that my octave was processing it like 3 to 5 minutes, and I think that's super annoying, and especially would make heck of a demo. I would have to whistle all along. So, based on those data, we get a flight profile. And this was provided by my ex-boss and colleague, so thanks. If you look at the flight profile, it's pretty characteristic for it's basically a missile. Nothing too strange about it. You can notice the period of getting to a certain speed or to a certain altitude in this case, cruising at predefined parameters and then homing for the target somewhere in this area. And another thing that I would like to show and give is a demo. Let's hope my laptop does not die. Yes. More or less. There is quite a disparity between what I expect when typing and what's happening now. Okay. So, okay. Here is a small, simple system rotating. Anybody interested in code can get it off me. And it's been written completely in Octave. Here there's just my small check to make sure that it's not that the reference frame is not in any way degrading over time, which can happen. Here you can take a look of basically what it is. It is the rotation matrices. I know that there are packages doing it probably better than me, but for this presentation I wanted to do it from scratch. Why not? And we can fiddle around with it. We can, for example, change a scale, give it some sort of acceleration. Don't ask me about the numbers, they're pretty much based on what I feel should be right. And if we cross our fingers and run it, yes, it did not explode. So the thing will start to move in space, and we still didn't lose orthogonality. So one final thought is on quaternions. Eventually, while redoing the lecture for the format, I decided to omit the quaternions as it would be too much math, but I just want to give you a food for thought what actually it is. It's widely used in 3D graphics, and it's super awesome. Again, it has two approaches, navigation and 3D vector graphics. If we go back to how we position our platform in Euler angles, what we do is we have a component of rotation. And each rotation can be separated into three components, yaw, pitch, roll. What quaternions do is take the shortcut and find the one perfect rotation that gets your system into place. And how they do it? By magic. It is basically a 4D system with three of the axes having -1 intensity, or it's having -1 intensity. Everything is called Hamiltonian space, so basically it transforms your physical coordinates into higher plane of reference, do some mathematical magic, which there is extremely elegant, so everything is multiplication and addition, unlike Euler angles where everything is sine, cosine, and if you get close to 90 degrees everything explodes. In quaternions you don't have that issue. Everything plays nice, but you have to transition into this abstract mathematical space construct. And when you transition to and from it, every single transition robs you a bit of precision. You can normalize and renormalize, but it will eventually accumulate and you will feel it as your system was losing orthogonality, for example. So that's all I had to say. Q&A.
Are there any questions?
Going once, going twice. Thanks a lot.